You've been told that space is a vast, empty void, but that idea is one of the strangest illusions in all of physics. Right now, in the gaps between the atoms of your body, in the space between you and the nearest wall, in the seemingly still darkness above the atmosphere, something is happening. Energy is flickering into existence and vanishing again, faster than light itself could ever report the news. What we call nothing is, on closer inspection, one of the most active and structured things we have ever tried to measure. And the strangest part is this: when physicists tried to calculate exactly how much energy that emptiness contains, they got an answer so wrong that it is often described as the single worst prediction in the history of science. Not wrong by a little, wrong by a factor followed by more zeros than most people will encounter in a lifetime. To understand why, we have to shrink ourselves down, past the edge of what the eye can see, past the edge of what atoms can see, into a realm where the rules of the universe start to behave, less like a stage and more like a substance. Start with something ordinary. Hold up your hand. It feels solid. It resists the air. It resists the table. It resists a closed fist. Every instinct built into your nervous system over hundreds of millions of years of evolution tells you that matter is continuous, dense, and unbroken. That instinct served our ancestors well when they needed to catch a spear or dodge a predator. It is also, at the level of atoms, almost entirely false. An atom is mostly emptiness. If you were to enlarge a hydrogen atom until its nucleus was the size of a marble sitting at the center of a large sports stadium, the single electron belonging to that atom would be found somewhere out near the stadium's outer seats, and everything in between would contain no matter at all. Scale that up to the entire human body, then to a wall, a mountain, a planet, and the conclusion becomes almost dizzying. The overwhelming majority of what we call solid reality is, in terms of raw occupied volume, more empty than the emptiest desert. What holds it together, what makes your hand feel solid when it presses against a table, is not matter touching matter. It is the electromagnetic force, specifically the repulsion between the electron clouds of your atoms and the electron clouds of the table's atoms, pushing back hard enough that neither surface can pass through the other. In other words, solidity itself is a kind of illusion generated by force fields, not by any continuous substance filling space. This realization about atoms did not arrive all at once. For most of the 19th century, physicists who accepted the existence of atoms at all tended to imagine them as small, dense, indivisible spheres, packed together with essentially no meaningful empty space between their internal parts. That picture was overturned in 1911, when the New Zealand-born physicist Ernest Rutherford, working with his students Hans Geiger and Ernest Marsden at the University of Manchester, fired a beam of positively charged particles at an extremely thin sheet of gold foil, only a few atoms thick, expecting the particles to pass through with only minor deflections, consistent with the prevailing model of the atom at the time, sometimes called the plum pudding model, in which negatively charged electrons were thought to be embedded throughout a diffuse, evenly distributed positive charge, like small pieces of fruit suspended within a pudding. Instead, while the great majority of particles did pass straight through the foil, largely undisturbed, a small fraction bounced back at sharp angles, some even reflecting almost directly backward toward the source. Rutherford later described this result as being about as believable as firing a large artillery shell at a piece of tissue paper and having it bounce back and hit you. The only explanation that fit the data was that almost all of the atom's mass and positive charge had to be concentrated in an extremely small, dense region at the center, a structure Rutherford named the nucleus, surrounded by a vast surrounding volume of largely empty space through which the lightweight electrons moved. Within just a few years, the Danish physicist Niels Bohr refined this picture further, proposing that electrons occupied specific quantized orbits around the nucleus rather than moving along arbitrary paths, an early and imperfect step toward the fuller quantum mechanical description of the atom that would follow over the next 2 decades. It is a nice piece of scientific history to keep in mind, because it shows that the discovery of empty space hiding inside solid-looking matter is not a brand new or fringe idea introduced by quantum field theory. It has been a settled and foundational part of physics for well over a century, and quantum field theory simply extended that same lesson, that appearances of solidity and emptiness can be deeply misleading, into the space between the atoms themselves. This alone should make you suspicious of the word empty. If the inside of matter is mostly field and almost no stuff, what does that say about the space between the stars, where there is no matter at all? For most of the history of science, the answer was simple: nothing. Literally nothing. The vacuum was defined, quite reasonably, as the absence of particles, the absence of pressure, the absence of anything that could be measured. Ancient philosophers argued for centuries about whether a true vacuum could even exist, with some insisting that nature abhorred it and that empty space was logically impossible. 17th century experimenters like Evangelista Torricelli and later Blaise Pascal built the first instruments capable of creating something close to a vacuum in a laboratory, using columns of mercury to demonstrate that air itself had weight and that a space could, in fact, be emptied of it. For roughly 3 centuries after that, the classical picture held firm. Space was the passive backdrop against which the drama of matter unfolded, a kind of infinite empty stage with no properties of its own beyond geometry. That picture nearly took a very different turn in the 19th century, when physicists studying light became convinced that space could not truly be empty after all, though for reasons that would later turn out to be entirely wrong. Light had been shown to behave as a wave, and every other wave scientists knew of, sound moving through air, ripples moving through water, needed a physical medium to travel through. This led to the proposal of a mysterious, invisible substance called the luminiferous ether, imagined as a rigid but undetectable medium filling all of space, through which light waves were thought to propagate the way sound propagates through air. The idea dominated physics for decades, until 1887, when Albert Michelson and Edward Morley designed an extraordinarily sensitive experiment intended to detect the Earth's motion through this supposed ether by measuring tiny differences in the speed of light traveling in different directions. The experiment found nothing, no difference at all, regardless of how the apparatus was oriented. This null result, one of the most famous in the history of science, quietly dismantled the ether hypothesis and helped set the stage for Albert Einstein's special theory of relativity in 1905, which did away with the need for any material medium entirely, showing that light could propagate through genuinely empty space without anything to carry it. For a brief window in scientific history, then, physicists had actually convinced themselves that space contained a hidden substance, only to have that specific idea firmly disproven. It is a useful piece of context, because it means the modern discovery that space is not simply empty after all did not emerge from repeating the old ether mistake. Quantum field theory arrived at a textured, active vacuum through an entirely different and far more rigorously tested route, one built on the mathematics of uncertainty rather than on the need for a mechanical medium to carry waves. Then, in the early 20th century, that stage started to misbehave. Quantum mechanics forced physicists to abandon the idea that particles are tiny, definite objects moving along smooth paths, the way a thrown ball moves through the air. Instead, particles began to look more like excitations, temporary ripples, in something called a quantum field, an invisible structure that fills all of space and time. Every type of particle in the universe, electrons, photons, quarks, has its own corresponding field spread out everywhere. And what we perceive as a particle is really just a localized vibration in that field. Similar to the way a single wave is a localized disturbance moving across the surface of an ocean that otherwise looks flat. This shift in perspective, from particles as tiny billiard balls to particles as field is the foundation of what is now called quantum field theory. Arguably the most successful and precisely tested framework in the history of physics, and it carries an enormous consequence for what we mean by empty space. If fields exist everywhere, then even a region containing zero particles still contains those fields. The fields simply exist in their lowest possible energy configuration, what physicists call the ground state, or more evocatively, the vacuum state. But here is where the story becomes genuinely strange, that ground state is not, and cannot be, perfectly calm. This is because of one of the most famous and most misunderstood ideas in modern science, the Heisenberg uncertainty principle, formulated by the German physicist Werner Heisenberg in 1927. Most people have heard a simplified version of it. Something like you cannot know both the position and the momentum of a particle with perfect precision at the same time. That is true, but the principle applies far more broadly than just position and momentum. It also applies to energy and time, and this particular pairing turns out to be the crack through which an entire hidden universe of activity pours through. The energy and time version of the uncertainty principle says, roughly, that over sufficiently short intervals of time, the energy of a system can be uncertain by a correspondingly large amount. It is not that we simply fail to measure the energy correctly. The energy genuinely is undefined, blurred, until the interval of time becomes long enough for the uncertainty to shrink towards zero. Put another way, absolute stillness, absolute zero energy, sustained forever, is forbidden by the basic mathematical structure of quantum theory. A field cannot simply sit at a flat, motionless, zero energy value the way a classical intuition might expect. It must fluctuate, tremble, and hum, even when there is nothing there to cause the trembling. If you were able to shrink down to the Planck scale, a length so small that a proton would look like a galaxy by comparison, you would not find calm nothingness. You would find something closer to a violent, roiling foam, a term physicist John Wheeler helped popularize in the 1950s to describe the predicted texture of space-time at its most fundamental scale. The Planck length, named after the German physicist Max Planck, who laid the foundations of quantum theory at the turn of the 20th century, is a distance so small that comparing it to an atom is almost meaningless, since it is smaller than an atom by roughly the same enormous ratio that an atom is smaller than the entire observable universe. At scales anywhere near this small are two great pillars of modern physics: quantum mechanics, which governs the very small, and general relativity, which governs gravity and the very large, are both expected to matter simultaneously, and neither theory on its own is currently capable of describing what actually happens there. Quantum mechanics predicts wild energy fluctuations at ever smaller scales, while general relativity teaches that concentrated enough energy warps space-time and can even form a black hole. Push the two theories together at the Planck scale, and the mathematics suggests that space-time itself may lose the smooth, continuous character we take for granted, dissolving instead into something closer to a chaotic, foaming, constantly fluctuating geometry, with tiny virtual black holes conceivably winking in and out of existence within the foam itself, an idea still firmly in the realm of theoretical speculation. since no experiment has ever probed distances remotely close to the Planck scale, which remains roughly 19 orders of magnitude smaller than anything even the Large Hadron Collider, the most powerful particle accelerator ever built, is capable of directly investigating. This gap between the smallest scale we can actually probe and the smallest scale our theories describe is one of the primary reasons why a complete, tested theory of quantum gravity has remained so elusive for so long. In this quantum foam, particle-antiparticle pairs are thought to appear together, borrow their existence briefly from the field's uncertainty budget, and then annihilate each other and vanish again, all within a span of time too short for any instrument ever built to directly witness. The particle-antiparticle pairing at the heart of this picture connects to one of the more dramatic origin stories in 20th century physics. In 1928, the British physicist Paul Dirac was attempting to write down an equation describing the electron that would be fully consistent with both quantum mechanics and Einstein's special relativity, something the earlier equations of quantum theory had failed to achieve properly. The equation he arrived at, now known as the Dirac equation, succeeded brilliantly, but it came within a deeply strange and initially unwelcome mathematical feature alongside solutions describing ordinary electrons with positive energy. The equation also produced an equal set of solutions describing particles with negative energy, a result that appeared at first to be a mathematical embarrassment rather than a physical prediction. Dirac, after considerable thought, proposed an audacious interpretation. Perhaps, he suggested, what we call empty space is not actually empty at all, but is instead completely filled with an infinite sea of these negative energy electron states, all already occupied, invisible to us precisely because there is no empty slot among them for an ordinary electron to fall into. This proposal, now remembered as the Dirac sea, further suggested that if enough energy was supplied to one of these hidden, filled negative energy states, an electron could be kicked out of it, leaving behind a hole in the sea that would behave from the outside exactly like a particle identical to the electron in every way except for carrying the opposite electric charge. Dirac had, without initially intending to, predicted the existence of antimatter. 4 years later, in 1932, the American physicist Carl Anderson, studying tracks left by cosmic ray particles passing through a cloud chamber at the California Institute of Technology, photographed exactly this kind of particle, a twin of the electron carrying positive rather than negative charge, which he named the positron. The modern picture of virtual particles constantly bubbling in and out of the vacuum, drawn from quantum field theory rather than Dirac's original negative energy sea, has since superseded the literal Dirac sea interpretation as the accepted explanation. But the historical episode remains a striking early example of exactly the pattern that runs through this entire story, taking the strange, uncomfortable mathematics of the vacuum seriously, rather than dismissing it, led directly to a genuine and experimentally confirmed discovery about the fundamental structure of reality. These are what physicists call virtual particles, and it is important to be precise about what that term actually means. Virtual particles are not simply theoretical placeholders, invented to make the mathematics easier. The way an accountant might use a temporary column in a spreadsheet, they are a real and necessary feature of how quantum fields interact. And while no virtual particle can ever be captured on its own the way a real particle can be captured in a detector, their collective influence on the world around them is measurable, repeatable, and precisely predicted by the equations of quantum electrodynamics, one of the most rigorously tested theories human beings have ever produced. Before we go further, here is worth pausing on something worth sitting with for a moment. This picture of the vacuum, a churning, energetic structure rather than a passive backdrop, is not a fringe idea or a speculative interpretation favored by only a handful of theorists. It sits at the very center of mainstream, mathematically verified physics, confirmed to extraordinary precision through decades of experiments in particle accelerators and precision laboratories around the world. If you find yourself wanting to understand this stranger, more textured version of reality in more depth, following along with how scientists actually test these ideas, rather than simply hearing about the headline conclusions, is one of the more rewarding habits a curious mind can build. So how do we know any of this is real, rather than just an elegant piece of mathematics that happens to produce correct-looking equations on a chalkboard? The answer involves one of the more elegant experiments in 20th century physics, first proposed by the Dutch physicist Hendrik Casimir in 1948. Casimir was working at the Philips Research Laboratories, thinking about strange discrepancies in how colloidal particles interacted with each other, when he arrived at a startling prediction. If you take two completely uncharged, perfectly conducting metal plates and place them extremely close together in a vacuum, close enough that the gap between them is measured in micrometers or even nanometers, the plates should experience a tiny but measurable force pulling them toward each other, with no external cause whatsoever, no electric charge, no gravity contribution large enough to matter at that scale, no wind, no field, no wire, just a plate in empty space, slowly drawn together by nothing. This is because of one of the most famous and most misunderstood ideas in modern science, the Heisenberg uncertainty principle, formulated by the German physicist Werner Heisenberg in 1927. Most people have heard a simplified version of it. Something like you cannot know both the position and the momentum of a particle with perfect precision at the same time. That is true, but the principle applies far more broadly than just position and momentum. It also applies to energy and time. And this particular pairing turns out to be the crack through which an entire hidden universe of activity pours through. The energy and time version of the uncertainty principle says, roughly, that over sufficiently short intervals of time, the energy of a system can be uncertain by a correspondingly large amount. It is not that we simply fail to measure the energy correctly. The energy genuinely is undefined, blurred, until the interval of time becomes long enough for the uncertainty to shrink toward zero. Put another way, absolute stillness, absolute zero energy, sustained forever, is forbidden by the basic mathematical structure of quantum theory. A field cannot simply sit at a flat, motionless, zero energy value the way a classical intuition might expect. It must fluctuate, tremble, and hum, even when there is nothing there to cause the trembling. If you were able to shrink down to the Planck scale, a length so small that a proton would look like a galaxy by comparison, you would not find calm nothingness. You would find something closer to a violent, roiling foam, a term physicist John Wheeler helped popularize in the 1950s to describe the predicted texture of space-time at its most fundamental scale. The Planck length, named after the German physicist Max Planck, who laid the foundations of quantum theory at the turn of the 20th century, is a distance so small that comparing it to an atom is almost meaningless, since it is smaller than an atom by roughly the same enormous ratio that an atom is smaller than the entire observable universe. At scales anywhere near this small, our two great pillars of modern physics, quantum mechanics, which governs the very small, and general relativity, which governs gravity and the very large, are both expected to matter simultaneously, and neither theory on its own is currently capable of describing what actually happens there. Quantum mechanics predicts wild energy fluctuations at ever smaller scales, while general relativity teaches that concentrated enough energy warps space-time and can even form a black hole. push the two theories together at the Planck scale. And the mathematics suggests that space-time itself may lose the smooth, continuous character we take for granted, dissolving instead into something closer to a chaotic, foaming, constantly fluctuating geometry, with tiny virtual black holes conceivably winking in and out of existence within the foam itself, an idea still firmly in the realm of theoretical speculation, since no experiment has ever probed distances remotely close to the Planck scale, which remains roughly 19 orders of magnitude smaller than anything even the Large Hadron Collider, the most powerful particle accelerator ever built, is capable of directly investigating. This gap between the smallest scale we can actually probe and the smallest scale our theories describe is one of the primary reasons why a complete, tested theory of quantum gravity has remained so elusive for so long. In this quantum foam, particle-antiparticle pairs are thought to appear together, borrow their existence briefly from the field's uncertainty budget, and then annihilate each other and vanish again, all within a span of time too short for any instrument ever built to directly witness. The particle-antiparticle pairing at the heart of this picture connects to one of the more dramatic origin stories in 20th century physics. In 1928, the British physicist Paul Dirac was attempting to write down an equation describing the electron that would be fully consistent with both quantum mechanics and Einstein's special relativity, something that earlier equations of quantum theory had failed to achieve properly. The equation he arrived at, now known as the Dirac equation, succeeded brilliantly, but it came with a deeply strange and initially unwelcome mathematical feature alongside solutions describing ordinary electrons with positive energy. The equation also produced an equal set of solutions describing particles with negative energy, a result that appeared at first to be a mathematical embarrassment rather than a physical prediction. Dirac, after considerable thought, proposed an audacious interpretation. Perhaps, he suggested, what we call empty space is not actually empty at all, but is instead completely filled with an infinite sea of these negative energy electron states, all already occupied, invisible to us precisely because there is no empty slot among them for an ordinary electron to fall into. This proposal, now remembered as the Dirac sea, further suggested that if enough energy was supplied to one of these hidden, filled negative energy states, an electron could be kicked out of it, leaving behind a hole in the sea that would behave, from the outside, exactly like a particle, identical to the electron in every way except for carrying the opposite electric charge. Dirac had, without initially intending to, predicted the existence of antimatter. 4 years later, in 1932, the American physicist Carl Anderson, studying tracks left by cosmic ray particles passing through a cloud chamber at the California Institute of Technology, photographed exactly this kind of particle, a twin of the electron carrying positive rather than negative charge, which he named the positron. The modern picture of virtual particles constantly bubbling in and out of the vacuum, drawn from quantum field theory rather than Dirac's original negative energy sea, has since superseded the literal Dirac sea interpretation as the accepted explanation. But the historical episode remains a striking early example of exactly the pattern that runs through this entire story, taking the strange, uncomfortable mathematics of the vacuum seriously rather than dismissing it, led directly to a genuine and experimentally confirmed discovery about the fundamental structure of reality. These are what physicists call virtual particles, and it is important to be precise about what that term actually means. Virtual particles are not simply theoretical placeholders invented to make the mathematics easier, the way an accountant might use a temporary column in a spreadsheet. They are a real and necessary feature of how quantum fields interact, And while no virtual particle can ever be captured on its own the way a real particle can be captured in a detector, their collective influence on the world around them is measurable, repeatable, and precisely predicted by the equations of quantum electrodynamics, one of the most rigorously tested theories human beings have ever produced. Before we go further, here is worth pausing on something worth sitting with for a moment. This picture of the vacuum, a churning, energetic structure rather than a passive backdrop, is not a fringe idea or a speculative interpretation favored by only a handful of theorists. It sits at the very center of mainstream, mathematically verified physics, confirmed to extraordinary precision through decades of experiments in particle accelerators and precision laboratories around the world. If you find yourself wanting to understand this stranger, more textured version of reality in more depth, following along with how scientists actually test these ideas, rather than simply hearing about the headline conclusions, is one of the more rewarding habits a curious mind can build. So how do we know any of this is real, rather than just an elegant piece of mathematics that happens to produce correct-looking equations on a chalkboard? The answer involves one of the more elegant experiments in 20th century physics, first proposed by the Dutch physicist Hendrik Casimir in 1948. Casimir was working at the Philips Research Laboratories, thinking about strange discrepancies in how colloidal particles interacted with each other, when he arrived at a startling prediction. If you take two completely uncharged, perfectly conducting metal plates and place them extremely close together in a vacuum, close enough that the gap between them is measured in micrometers or even nanometers, the plates should experience a tiny but measurable force pulling them toward each other with no external cause whatsoever, no electric charge, no gravity contribution large enough to matter at that scale. No wind, no field, no wire. Just two plates in empty space, slowly drawn together by nothing. A different but related confirmation comes from an effect called vacuum birefringence, and it involves some of the most extreme objects known to exist in the universe. A rare class of neutron star possessing magnetic fields trillions of times stronger than anything producible in any laboratory on Earth. Quantum electrodynamics predicts that in the presence of an extraordinarily powerful magnetic field, the vacuum itself should begin to behave, very slightly, like an unusual optical material, causing different polarizations of light passing through that region of space to travel at very slightly different effective speeds, an effect called birefringence, normally associated with certain crystals rather than empty space. In 2016, an international team of astronomers led by Roberto using the European Southern Observatory's Very Large Telescope in Chile, measured polarized visible light coming from a nearby neutron star known as RxJ 1856.5-3754, and found a level of polarization consistent with a prediction of vacuum birefringence caused by the star's immense magnetic field acting on the surrounding empty space. While follow-up observations and theoretical interpretation of this specific measurement have continued to be refined and debated within the astrophysics community, the underlying prediction itself, that a sufficiently powerful magnetic field can measurably distort the vacuum's optical properties, remains a well-established consequence of quantum electrodynamics, offering yet another independent thread of evidence, this time written across the light arriving from a collapsed star many hundreds of light years away, that the vacuum is an active physical medium rather than a truly featureless void. This is worth dwelling on, because it represents something genuinely rare in science, a prediction born entirely from abstract mathematics about the structure of nothingness, confirmed decades later by an experiment that physically moved objects in a laboratory. The vacuum was no longer simply a theoretical convenience. It had muscles, And if the vacuum has muscles, the next question becomes almost unavoidable. How strong are they? If quantum fields never truly rest, if every patch of space is constantly generating and reabsorbing energy through fluctuation, then space itself should possess an intrinsic energy density, an amount of energy packed into every cubic unit of nothingness, everywhere, at all times, forever. This is where the story of the vacuum collides head-on with the story of the universe's expansion, and where one of physics' proudest theoretical frameworks produced one of its most embarrassing numerical failures. In 1998, two independent teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were using distant exploding stars called Type 1, a supernova, as cosmic mile markers to measure how the expansion of the universe had changed over billions of years. The expectation, based on the gravitational pull of all the matter in the cosmos, was that the expansion should be slowing down over time, the way a ball thrown upwards slows as gravity pulls it back. Instead, both teams found the opposite. The expansion of the universe was speeding up. Something was pushing galaxies apart faster and faster, working against gravity on the largest scales imaginable. This discovery, which earned the three scientists the Nobel Prize in Physics in 2011, demanded an explanation, and the leading candidate then and now carries the almost deliberately mysterious name dark energy. There is a strange twist of history buried inside this story that makes it even more remarkable. Decades earlier, in 1917, Albert Einstein himself had introduced a term into his newly developed equations of general relativity called the cosmological constant, represented by the Greek letter lambda. At the time, Einstein was not thinking about accelerating expansion at all. Astronomers of that era believed the universe was static, neither expanding nor contracting, existing in a kind of eternal equilibrium. And Einstein found that his original equations predicted a universe that should inevitably collapse or expand under its own gravity. Contradicting that assumption, to force his equations to describe a static universe, he added the cosmological constant as a kind of counterbalancing, repulsive term, a mathematical patch inserted purely to prevent gravitational collapse. Just over a decade later, in the late 1920s, the American astronomer Edwin Hubble, building on observations of distant galaxies, demonstrated that the universe was not static at all, but was expanding, with galaxies rushing away from each other in every direction. With that discovery, Einstein's original motivation for the cosmological constant evaporated, and he reportedly referred to introducing it as one of the greatest blunders of his career, later dropping it from his equations entirely. For roughly 70 years, the cosmological constant sat largely abandoned in physics textbooks, treated as a historical curiosity, an unnecessary complication that a wiser Einstein had wisely discarded. Then, in 1998, the discovery of accelerating expansion brought it roaring back from retirement, not as a device for preventing expansion, but as one of the leading candidates for explaining why expansion itself was speeding up. What Einstein had once considered his greatest mistake turned out, in a different form, to closely resemble one of the most important terms in modern cosmology. One of the most natural candidates for dark energy is the energy of the vacuum itself. If empty space is not truly empty, if it carries its own intrinsic energy density from those constant quantum fluctuations, then more space means more total energy. And as the universe expands, that energy could act as a kind of repulsive pressure, gently pushing everything apart. This is, conceptually, an elegant idea. Space itself provides the fuel for its own expansion. The trouble began when physicists actually tried to calculate the size of that vacuum energy using quantum field theory, and compared the result against what astronomers had measured from the accelerating expansion of the universe. The theoretical calculation, summing up the contributions of all known quantum fields fluctuating at all possible energy scales up to the Planck scale, produces a number 4 vacuum energy density that is staggeringly, almost comically large. The observed value, inferred from the actual behavior of the accelerating cosmos, is vastly smaller. The mismatch between these two numbers is not a rounding error or a matter of missing a decimal point here and there. It spans somewhere in the neighborhood of 120 orders of magnitude, a number so large it resists ordinary intuition entirely. To put a number that size into some kind of perspective, if you tried to represent the discrepancy as a single figure with a 1 followed by zeros, you would need more zeros than there are atoms in every star, planet, and grain of dust in the observable universe combined. Several times over, nothing else in the history of quantitative science comes remotely close to this level of disagreement between theoretical prediction and observed reality. It has become known, half wryly and half with genuine professional embarrassment among theoretical physicists, as the cosmological constant problem, and it is frequently cited as the worst theoretical prediction in the history of physics. It is worth being precise here about what is settled and what remains an open puzzle, because it would be easy to let the sheer scale of the discrepancy slide into either false certainty or unwarranted despair. The existence of the accelerating expansion is not in serious scientific dispute. It has been confirmed through multiple independent lines of evidence beyond the original supernova observations, including detailed studies of the cosmic microwave, background radiation by missions such as the European Space Agency's Planck satellite, and large-scale surveys mapping the distribution of galaxies across billions of light-years. What remains genuinely uncertain is the underlying cause. Vacuum energy, formally represented in Einstein's equations of general relativity by a term called the cosmological constant, is the leading and simplest candidate, requiring the fewest additional assumptions. But alternative explanations exist and are actively studied, including the possibility of a dynamical field, sometimes called quintessence, whose energy density changes over cosmic time rather than remaining fixed, or the more radical possibility that our understanding of gravity itself breaks down at the largest cosmic scales and needs modification. Distinguishing between these options is one of the primary goals driving current and upcoming observational efforts, including the European Space Agency's Euclid mission and the American Vera C. Rubin Observatory, both designed to map the distribution and behavior of matter and energy across cosmic history with unprecedented precision, specifically to determine whether dark energy has remained perfectly constant or has subtly evolved. This is not a purely hypothetical question anymore, and it is one of the clearest examples currently available of frontier cosmology being conducted in full public view, with preliminary results, open datasets, an ongoing scientific debate all unfolding in real time rather than emerging only after decades of quiet, closed-door analysis. In March of 2025, the collaboration behind the Dark Energy Spectroscopic Instrument, a ground-based survey mounted on the Mayol telescope at Kitt Peak National Observatory in Arizona, released results built from 3 years of observations covering millions of galaxies and quasars stretching back across roughly 11 billion years of cosmic history. When those measurements were combined with independent data from the cosmic microwave background, from supernova surveys, and from studies of how gravity subtly bends light traveling from distant galaxies, a pattern emerged that had not been strongly present in earlier, smaller datasets. The strength of dark energy's push against gravity appeared, statistically, to be gently weakening over the past several billion years, rather than remaining perfectly fixed as the simplest vacuum energy model would require. It is important to describe this result with appropriate caution and precision, since that is exactly how the collaboration itself has described it. The evidence, while described by many cosmologists as unusually compelling for a result of this kind, has not yet crossed the extremely high statistical threshold that particle physicists and cosmologists traditionally require before declaring a genuinely new discovery rather than a strong hint. If the pattern holds up and strengthens as more data arrives from Euclid, from the Vera C. Rubin Observatory's legacy survey of space and time, and from continued observing seasons of the dark energy spectroscopic instrument itself, it would represent a genuinely significant shift, effectively ruling out the simplest possible explanation for cosmic acceleration, the idea of a perfectly fixed vacuum energy density, and pointing, instead, towards some kind of dynamical field or evolving physical mechanism behind the acceleration of the universe. It is a vivid, current example of science actively working in real time on one of the exact questions this documentary has been exploring. Is the energy of empty space a fixed, unchanging property of the vacuum, or something closer to a slowly shifting field with a history and a future of its own? Meanwhile, on the theoretical side, physicists have spent decades trying to understand why the naive calculation of vacuum energy overshoots reality by such an extreme margin. One line of reasoning proposes that some deeper, currently unknown symmetry or cancellation mechanism suppresses almost all of the predicted vacuum energy, leaving behind only the tiny residual sliver that we actually observe driving cosmic acceleration, in the same way that two enormous numbers can subtract to leave a small remainder if they happen to be almost, but not quite, equal. Finding a convincing, mathematically consistent reason for such a cancellation, without simply assuming it by hand, has proven to be one of the most stubborn, unsolved problems in fundamental theoretical physics, touching on quantum gravity, string theory, and the search for a framework that can unite quantum mechanics with general relativity. Some theorists have even explored the controversial idea that the small observed value might not have a deep dynamical explanation at all, but instead reflects a kind of selection effect. Perhaps our universe is one of an enormous number of possible universes, each with different fundamental constants, and only universes with a vacuum energy small enough to permit galaxies, stars, and eventually observers to form would ever have anyone around within them to notice the puzzle in the first place. This idea, often associated with the broader and still hotly debated multiverse hypothesis and sometimes framed through what is called anthropic reasoning, remains speculative and is not universally accepted within the physics community, precisely because it is extraordinarily difficult to test using any conceivable experiment. It is included here not as an established answer, but as an honest reflection of how unresolved this territory still is. What is not in serious dispute is this: the vacuum of space carries genuine physical energy. That energy has real, measurable consequences both in laboratory experiments like the Casimir effect and on the scale of the entire observable cosmos. And our current theoretical tools, despite their extraordinary success in almost every other domain of physics, from predicting the magnetic properties of the electron to 9 decimal places, to guiding the discovery of the Higgs boson at the Large Hadron Collider in 2012, fail spectacularly when asked to predict the size of that vacuum energy. It is a rare and humbling situation, the same mathematical machinery that got nearly everything else right gets this one number wrong by more than 100 orders of magnitude. It is worth pausing to appreciate just how unusual this combination is within the broader history of physics. Ordinarily, when a theory fails, it fails cleanly, producing predictions that clash with experiment across the board. prompting scientists to discard or heavily revise the theory in question. The way the ether hypothesis was eventually abandoned once the Michelson-Morley result came in. Quantum field theory has not failed in that clean, easily dismissed way. It continues to produce the most accurate predictions in the history of experimental science for an enormous range of phenomena. From the magnetic moment of the electron to the detailed behavior of particles inside the Large Hadron Collider. And yet, when the very same framework is pointed at the total energy content of empty space itself, it produces an answer wildly disconnected from what telescopes actually observe happening to the universe. This strange, split personality, spectacularly successful in some domains, and spectacularly wrong in one very specific, but very fundamental calculation, is part of what convinces many physicists that the cosmological constant problem is not simply a matter of needing more decimal places or more careful bookkeeping. It looks, instead, like a genuine signal that some deeper piece of physics, not yet incorporated into the standard framework, is quietly at work, cancelling away almost the entirety of the naively predicted vacuum energy through some mechanism still unknown, leaving behind only the faint residual whisper of acceleration that Schmidt and Rees first detected in the light of distant exploding stars. That combination of extraordinary success and extraordinary failure, occurring within the very same theoretical framework, is part of what makes the vacuum such a compelling frontier of modern physics. It is simultaneously the best understood and the least understood substance in the universe, given how strange and structured the vacuum already appears through quantum field theory alone. Some physicists have pursued an even more radical one that borrows its language and mathematics, not from cosmology, but from an entirely different branch of physics, the study of solids, crystals, and condensed matter here on Earth. This is genuinely speculative territory, sitting well outside the mainstream consensus model, and it is important to be clear about that distinction from the outset. But it is a serious and mathematically active line of theoretical inquiry, not idle fantasy, and it offers one of the more mind-bending ways to think about what empty space might actually be. The core idea, sometimes discussed under names like superfluid vacuum theory or analog gravity, begins with an observation about materials here on Earth. Consider a superfluid, a special quantum state of matter, first observed in 1937 independently by the Soviet physicist Pyotr Kapitsa and separately by the Canadian and British duo John Allen and Don Misner, working with liquid helium cooled to within a few degrees of absolute zero. At those temperatures, ordinary liquid helium undergoes a striking transformation. It stops behaving like a normal fluid entirely and instead begins to flow with zero viscosity, no internal friction whatsoever, capable of climbing up and over the walls of its own container in a thin film, seemingly defying gravity, and capable of flowing forever through narrow channels that would instantly stop any ordinary liquid. Kapitsa's careful low-temperature experiments earned him a share of the Nobel Prize in Physics in 1978, decades after the original discovery, for uncovering this genuinely new state of matter. Or consider a Bose-Einstein condensate, an even more extreme, exotic state of matter, first predicted theoretically in the 1920s by Satyendra Nath Bose and Albert Einstein, but not actually created in a laboratory until 1995, when Eric Cornell and Carl Wieman, working at the University of Colorado Boulder, successfully cooled a dilute cloud of rubidium atoms to a temperature only a few billionths of a degree above absolute zero, colder than anywhere else known to exist in the universe, including the depths of interstellar space. At that temperature, the individual atoms lose their separate identities and begin behaving as a single, unified quantum entity described by one collective wave function, a genuinely new and almost eerie state of matter that earned Cornell, Wien, and fellow physicist Wolfgang Ketterol the Nobel Prize in Physics in 2001. In both of these states of matter, the medium itself possesses a kind of underlying microscopic structure, even though on a large scale it can appear smooth, continuous, and featureless, much the way a calm ocean surface hides the immense complexity of the water molecules beneath it. Disturbances moving through us, ripples, vortices, and quasi-particles, behave in remarkably similar mathematical ways to how particles behave when moving through the quantum vacuum of empty space. This resemblance has led a subset of theoretical physicists to explore the speculative possibility that the vacuum of the universe might itself be some kind of underlying medium, a background substance with its own microscopic degrees of freedom that we simply have not yet detected or resolved, out of which what we perceive as fundamental particles emerge as collective excitations, similar to the quasi-particles and defects that emerge from the underlying atomic lattice inside an ordinary crystal. In an ordinary crystal, imperfections in the otherwise regular lattice arrangement of atoms, things like missing atoms, misaligned rows, or twisted regions, are called defects, and they behave in many ways like independent particles moving through the material, even though they are really just patterns of disturbance in the underlying lattice rather than separate objects in their own right. The provocative suggestion explored in these speculative frameworks is that electrons, quarks, and photons might, at some deeper level not yet accessible to our experiments, be analogous to defects or excitations propagating through a more fundamental substrate, rather than truly elementary and structureless entities in their own right. It is worth being very direct about the current scientific status of this idea. There is, as of now, no confirmed evidence that the vacuum possesses an actual crystalline or lattice-like microstructure in the literal sense that ordinary matter does, and this remains a minority and highly speculative research direction rather than an established discovery. No experiment has detected the kind of underlying grain or lattice spacing that would be the smoking gun signature of such a structure. And many physicists working in mainstream quantum field theory and string theory pursue entirely different approaches to unifying gravity with quantum mechanics that do not rely on this condensed matter analogy at all. What makes the idea worth discussing honestly, rather than dismissing outright, is that it connects to a genuinely mainstream and well-studied phenomenon called an analog gravity system, in which physicists build laboratory setups, often using flowing fluids, cooled atomic gases, or engineered optical materials that mathematically mimic certain behaviors of curved spacetime and even black hole event horizons, without involving actual gravity at all. In 2019, physicist Jeff Steinhauer and colleagues reported creating a laboratory analog of Hawking radiation, the theoretical process by which black holes are predicted to slowly emit particles and lose mass over immense timescales, using a Bose-Einstein condensate engineered to mimic the mathematical structure of a black hole's event horizon. These analog experiments do not prove that real spacetime is literally built from an underlying condensed matter substance, but they do demonstrate that the mathematics describing exotic quantum materials and the mathematics describing curved spacetime share a genuine, non-coincidental structural resemblance, which is precisely why some theorists take the deeper analogy seriously as a possible clue rather than dismissing it purely as a coincidence. The connection to Hawking radiation is worth dwelling on a little longer, because it ties this entire condensed matter analogy directly back to the vacuum fluctuations discussed earlier in an unexpectedly elegant way. In 1974, The British physicist Stephen Hawking made a discovery that surprised almost everyone in theoretical physics, including, by his own account, Hawking himself. Working through the implications of applying quantum field theory to the curved spacetime surrounding a black hole, he found that black holes should not be perfectly black after all, very close to a black hole's event horizon, the boundary beyond which nothing, not even light, can escape. The same virtual particle pairs that constantly flicker in and out of existence throughout ordinary empty space can occasionally be split apart by the black hole's intense gravitational field before they have a chance to recombine and annihilate each other. One member of the pair falls into the black hole, while the other escapes outward as real, detectable radiation, carrying away a small amount of the black hole's mass and energy in the process, over spans of time vastly longer than the current age of the universe. This process implies that black holes should slowly evaporate, losing mass bit by bit until, in the extremely distant future, they vanish entirely, releasing their remaining energy in a final burst. Hawking radiation from real astrophysical black holes remains far too faint to have ever been directly detected, since the predicted radiation from a black hole of stellar mass would be colder than the background temperature of the universe itself, making it functionally invisible against the ambient noise of the cosmos. A technical limitation rather than any weakness in the underlying theoretical reasoning that led Hawking to the prediction in the first place. This is precisely why laboratory analog experiments, like the Bose-Einstein condensate black hole analog built by Jeff Steinhauer's team, matter so much. They cannot fully replicate genuine gravitational physics, but they can test the underlying quantum field theory mechanism, the splitting of vacuum fluctuation pairs at an effective horizon, in a setting where the resulting radiation is strong enough to actually measure, offering indirect but meaningful support for one of Hawking's most famous and still unconfirmed theoretical predictions. Related to this line of thinking is the idea that the vacuum itself might not be a single, fixed, unchanging state across the entire history of the universe, but rather one particular phase among several possible configurations, capable in principle of transitioning from one phase to another under the right conditions, much the way water can exist as ice, liquid, or vapor depending on temperature and pressure. This is not merely a poetic metaphor. It connects to genuinely established physics through the concept of spontaneous symmetry breaking and the mechanism, developed independently in the 1960s by physicists including Peter Higgs, Robert Brout, and Francois Englert, that explains why certain particles have mass at all, according to the standard model of particle physics, confirmed experimentally with the discovery of the Higgs boson at the Large Hadron Collider in 2012. An invisible field called the Higgs field permeates all of space, and it did not always have the particular configuration it has today. In the earliest fractions of a second after the Big Bang, when the universe was almost inconceivably hot, the Higgs field is believed to have existed in a different, more symmetric state, one in which the particles we now think of as fundamentally massive, like the electron, the quarks, and the W and Z bosons that carry the weak nuclear force, would have been effectively massless. As the universe expanded and cooled below a critical temperature, the Higgs field underwent what is called a phase transition, settling into its current lower energy configuration, and in doing so, it began interacting with other particles in a way that endows them with the mass we measure today. In this very real and experimentally supported sense, the vacuum of our universe has already, at least once in cosmic history, undergone something functionally similar to a phase change, altering the basic properties of matter as a direct result. There is an unsettling corollary to this idea of the vacuum as a phase of matter. one that has attracted serious attention from theoretical physicists precisely because it follows so directly from well-established physics rather than exotic speculation. If our current vacuum state is simply one configuration among several possible ones, the question naturally arises of whether it is the lowest energy configuration available, the true, stable, permanent ground state of the universe, or whether it might instead be what physicists call a false vacuum, a state that is stable enough to persist for an extremely long time, but which is not actually the lowest possible energy state the universe could occupy. The analogy often used is a ball resting in a shallow dip partway down a hillside. The ball appears stable, and for all practical purposes it is, sitting quietly without any nearby force to dislodge it. But further down the hill lies a much deeper valley, a true minimum, and if the ball were ever given a sufficient nudge, it would roll past the lip of its shallow dip and tumble down into that lower state, releasing a burst of energy in the process. Long before physicists worried about the vacuum decaying away in the distant future, a strikingly similar idea was already playing a central role in explaining the universe's distant past. In 1980, the American physicist Alan Guth proposed a theory called cosmic inflation to solve several nagging puzzles about the large-scale structure and uniformity of the universe that the standard Big Bang model, on its own, struggled to explain convincingly. Guth's proposal centered on the idea that in an extraordinarily brief window at the very beginning of cosmic history, likely less than a tiny fraction of a second after the Big Bang itself, the universe passed through a state resembling exactly the kind of false vacuum described above, a region of space temporarily trapped in a higher energy configuration rather than settling immediately into its true, lower energy ground state. While trapped in that unstable configuration, the energy of the false vacuum would have acted, according to the equations of general relativity, as an immense repulsive pressure, driving an almost incomprehensibly rapid exponential expansion of space itself, stretching the universe by a factor of many trillions of trillions within a span of time, far too short for light to cross even the width of a single atom. When this inflationary false vacuum state eventually decayed into the true, lower energy vacuum, the enormous energy difference between the two states would have been released in a burst, filling the newly expanded universe with the hot, dense soup of particles that conventional Big Bang cosmology describes evolving from that point onward. In this picture, the very same physics of vacuum states, false configurations, energy differences, and decay that shows up in speculative discussions of the far future also appears to be central to explaining the origin of the universe's structure in the extreme past, and predictions arising from inflationary theory, particularly regarding the detailed statistical pattern of tiny temperature variations imprinted on the cosmic microwave background, had been tested with considerable success by missions including the Wilkinson microwave, anisotropy probe, and the European Space Agency's Planck satellite. Inflation remains an active area of research rather than a fully settled theory, with several competing detailed models still under investigation and some specific predictions still awaiting confirmation. Particularly the search for a predicted background of primordial gravitational waves that a future generation of instruments, potentially including the laser interferometer space antenna, may eventually be sensitive enough to detect, applied to the vacuum itself. This idea was developed in rigorous mathematical form during the 1970s and 80s, most notably by the physicist Sidney Coleman, who worked out the theory of how a false vacuum could, in principle, decay. According to this framework, a small bubble of true, lower energy vacuum could spontaneously form somewhere in space through a process called quantum tunneling, an inherently probabilistic quantum event that could, in an idealized model, happen at literally any location and at any moment, with no advance warning whatsoever. If such a bubble formed, the laws of physics inside it, the masses of particles, the strengths of forces, potentially even the number of stable dimensions, could differ from the laws we currently experience. And critically, once formed, such a bubble would not stay contained. According to the theory, it would expand outward in every direction at a speed approaching the speed of light itself, converting everything it touched into the new vacuum state as it went, with no possible way to detect its approach beforehand, since nothing, including light, could outrun the boundary of the expanding bubble once it began growing. It is important to be extremely clear about the actual scientific status of this idea, because it is exactly the kind of concept that tends to get sensationalized well beyond what the evidence supports. Current measurements of the mass of the Higgs boson, combined with a measured mass of the top quark, the heaviest known fundamental particle, place the properties of our universe's vacuum in a region of the theoretical landscape that calculations suggest may technically be meaning a lower energy, true vacuum state might exist in principle. However, even under this scenario, the calculated timescale over which such a decay might be expected to occur, purely through spontaneous quantum tunneling with no external trigger, is staggeringly longer than the current age of the universe, vastly longer, in fact, than almost any other timescale discussed in cosmology. Multiple independent groups of physicists studying this question have been consistent in stressing that there is no cause for concern on any timescale remotely relevant to human civilization, or even to the remaining lifespan of the Sun. The value of the false vacuum decay concept lies not in any genuine near-term risk, but in what it reveals about how physicists think about the vacuum today, not as a fixed, eternal backdrop, but as a specific state of a dynamical field, a state that in principle carries its own physics of stability, decay, and transition, the same way any other physical configuration might. There is a related and genuinely surprising fact about the vacuum that rarely makes it into popular discussions of the Higgs field, and it concerns something as basic as the mass of your own body. It is a common assumption that the Higgs mechanism is responsible for essentially all of the mass we encounter in everyday life. But that assumption turns out to be significantly wrong. The protons and neutrons that make up the nucleus of every atom in your body are not fundamental particles. Each one is built from 3 smaller particles called quarks, bound tightly together by the strong nuclear force. The Higgs field does contribute a small amount of mass to each individual quark, but when physicists carefully add up the masses of the 3 quarks inside a proton, the total comes to only a small fraction, roughly around 1% of the proton's actual measured mass. The remaining 99% or so does not come from the Higgs field at all. It comes from the vacuum of the strong nuclear force itself, described by a theory called quantum chromodynamics, in which the force binding quarks together grows stronger, rather than weaker, as the quarks are pulled farther apart, an unusual property called confinement that has no equivalent in ordinary electromagnetism. The energy required to hold the quarks together against this force, energy stored in the surrounding field itself, in the churning vacuum of gluons, the particles that carry the strong force, converts through Einstein's famous relationship between mass and energy into the overwhelming majority of a proton's actual mass. In other words, when you feel the weight of your own body, you are, in a very real and quantitatively precise sense, feeling mostly the energy of a different, more violent corner of the quantum vacuum. Not the Higgs field most popular science coverage tends to credit with the job. It is one of the more genuinely startling facts to emerge from 20th century particle physics, that the solid heft of ordinary matter is, at its foundation, mostly an artifact of vacuum energy rather than the intrinsic mass of any fundamental particle at all. This raises a genuinely open and actively researched theoretical question. Could similar phase transitions have happened at other points in cosmic history, at even higher energies than the Higgs transition? Perhaps unifying forces that today appear separate, like the electromagnetic force and the weak nuclear force, or even, at higher energies still, the strong nuclear force alongside them, in frameworks known as grand unified theories. And could the properties of empty space that we currently measure, the strength of gravity, the mass of the electron, the specific value of the vacuum energy driving cosmic acceleration, actually be closer to local settings within our particular corner of a much larger and more varied cosmic landscape, rather than truly universal and unchangeable constants of nature? These questions sit at the very edge of testability, some perhaps permanently beyond direct experimental reach, and it is honest to say that physicists disagree substantially about how seriously to take them. But they emerge naturally and logically from established, experimentally confirmed physics, namely the reality of the Higgs mechanism and the reality of spontaneous symmetry breaking, rather than being invented from nothing. Stepping back from the specific, speculative frontiers, a broader and much more solidly established picture comes into focus, one that ties everything discussed so far into a single coherent story about the architecture of reality. The properties of the vacuum are not incidental background details. They are, in a very real sense, the source code determining nearly everything about the physical world we experience. The Higgs field's particular configuration in the vacuum determines the mass of the electron, and that mass, in turn, determines the size of atoms. Since the way electrons arrange themselves in orbitals around a nucleus depends directly on their mass, the size of atoms determines the chemistry that is possible, which molecules can form, which reactions can occur, which structures, from proteins to planets, are stable enough to exist. Change the vacuum's properties, even slightly, and the entire chain of consequences that follows: chemistry, biology, the possibility of stars burning stably for billions of years, the possibility of planets forming at comfortable distances from those stars, could unravel entirely. The vacuum, far from being an empty stage on which the true actors of the universe, matter and energy, perform their drama, increasingly looks like it might be the deepest and most consequential actor of all, quietly setting the rules that every other actor must obey. There is one more thread worth pulling on before moving forward, because it connects the extreme fine-tuning of the vacuum's energy to an even broader pattern that physicists and cosmologists have long found unsettling. The cosmological constant is not the only fundamental quantity in physics that appears to be balanced with what looks, at least superficially, like suspicious precision. The relative strengths of the four fundamental forces, the precise mass of the electron compared to the proton, the exact ratio between the strength of gravity and the strength of electromagnetism, all seem to sit within surprisingly narrow ranges that happen to permit stable atoms, long-lived stars, and complex chemistry to exist at all. Shift several of these numbers by even a modest percentage in either direction, and calculations suggest that stars might burn out too quickly to allow life-bearing planets to develop, or that atomic nuclei might be too unstable to form the rich variety of elements that make chemistry, and therefore biology, possible in the first place. This broad pattern is often referred to as the fine-tuning problem, and it has produced two very different families of response within the scientific and philosophical community. One response, associated with the multiverse hypothesis and often paired with eternal inflation, a theoretical extension of the widely accepted Big Bang inflationary model developed by physicists including Alan Guth and Andre Lind in the early 1980s, proposes that our observable universe might be just one bubble among an enormous, perhaps infinite, number of separate regions, each forming through its own local end to an eternally inflating background, and each potentially settling into a different random vacuum state with its own distinct physical constants. Under this view, life and observers would naturally only ever arise within the rare bubbles whose local constants happened to permit it, making our own finely tuned surroundings far less surprising once the full statistical landscape is taken into account. A form of reasoning called the anthropic principle. The competing response holds that invoking an enormous number of unobservable universes to explain fine-tuning trades, one mystery for a much larger and even less testable one, and that physicists should instead continue searching for a single, deeper underlying principle or symmetry that would explain why the constants of our universe take the specific values they do, without needing to appeal to chance or selection across a landscape of alternate realities at all. Neither position currently commands anything close to universal agreement among physicists, and it is worth being upfront that this entire debate sits closer to the philosophical edge of physics than to its experimentally confirmed core, precisely because testing the existence of other universes, by definition regions we can never observe or interact with, may not be achievable even in principle. It is included here not because it resolves anything, but because it shows how directly the specific narrow puzzle of the vacuum's energy connects to some of the largest and most contested questions in all of modern cosmology. This reframing carries provocative implications for the future of physics and technology, though it is important to distinguish clearly at every step between what current physics actually supports and what remains firmly in the realm of speculation, since this is an area where popular science writing has historically overpromised and misled. The Casimir effect, being a real, measured, and repeatable phenomenon, has already found modest, practical relevance in the design of microelectromechanic systems, tiny mechanical devices built at scales small enough that quantum vacuum forces between closely spaced components can actually interfere with their intended operation, requiring engineers to account for it. In devices such as microscopic accelerometers, tiny mirrors, and switches manufactured at scales measured in millionths of a meter, moving components can sometimes drift close enough together that the Casimir force causes them to stick together permanently. A failure mode engineers have come to call stiction. And understanding the underlying vacuum physics has become a genuinely practical concern for the field of nanotechnology rather than a purely academic curiosity. Researchers, including groups led by physicist Federico Capelli, first at Bell Laboratories and later at Harvard University, have gone further still, exploring whether the Casimir force can be engineered rather than merely tolerated, showing experimentally that under specific geometric arrangements and using carefully chosen materials, the normally attractive Casimir force between two surfaces can, remarkably, be made to reverse and become repulsive instead, opening possible avenues for building microscopic and nanoscale machines that could, in principle, use quantum vacuum forces as a working design tool rather than treating them purely as an unwanted nuisance to engineer around. Some researchers have explored, at a purely theoretical and highly preliminary level, whether deliberately engineered vacuum fluctuations might one day be harnessed for extremely small-scale propulsion or actuation at the nanoscale, though nothing resembling the vacuum energy propulsion systems sometimes depicted in speculative fiction has any established grounding in tested physics, and most physicists working in the field would characterize such applications as, at best, an extremely distant and uncertain possibility rather than a near-term engineering goal. It is worth being candid about this, since the temptation to overstate the practical implications of frontier physics is strong, and doing so does a disservice to how genuinely interesting the confirmed science already is on its own terms. It is also worth addressing, directly and honestly, a category of claims that circulates widely outside of mainstream physics: the idea that so-called zero-point energy, the residual quantum fluctuation energy present even in a vacuum's lowest possible state, could be tapped as a limitless, free source of usable power. This idea has attracted attention from inventors and fringe researchers for decades, occasionally attached to claimed devices or patents promising energy extraction from empty space itself. It is important to state clearly that no such device has ever been demonstrated to work under controlled, independently verified conditions, and the overwhelming consensus among physicists is that doing so would violate basic thermodynamic principles that have never once been shown to fail in any other tested context. The Casimir effect, for comparison, does not generate usable net energy from nothing. It involves a one-time redistribution of force resulting from a specific, carefully engineered geometry, and does not offer any means of continuously extracting power. Being honest about this distinction matters, because the real, measured strangeness of the quantum vacuum is remarkable enough, on its own terms, without needing exaggerated claims to make it interesting. And conflating legitimate quantum field theory with unproven energy extraction schemes does a disservice to both. What can be said with much greater confidence is that our understanding of the vacuum continues to shape the direction of fundamental research across multiple major branches of physics simultaneously. In particle physics, experiments at facilities like the Large Hadron Collider continue to probe the detailed structure of the Higgs field and search for possible additional particles or symmetries that might help explain why the vacuum energy prediction and the vacuum energy observation differ so extraordinarily. In cosmology, missions mapping the cosmic microwave background and the large-scale structure of galaxies continue refining our measurement of dark energy's behavior over cosmic time, searching for any subtle hint that it has changed rather than remained perfectly constant. A discovery that would rule out the simplest vacuum energy explanation and point toward something more dynamic. In condensed matter physics, laboratories continue building and refining analog gravity systems using ultra-cold atoms and engineered materials, testing whether the deep mathematical parallels between exotic states of matter and curved space-time reflects something more than coincidence. And in theoretical physics, more broadly, the search for a framework unifying quantum mechanics with general relativity, whether through string theory, loop quantum gravity, or approaches not yet invented, continues to treat the cosmological constant problem as one of its central guiding puzzles, precisely because any successful theory of everything will eventually need to explain why the vacuum weighs as little as it does, rather than as much as the naive calculation predicts. It is worth taking a moment to look more closely at these two leading, though still unproven, candidate frameworks for unifying gravity with quantum mechanics, since each treats the vacuum in a strikingly different way, and the eventual choice between them, or the discovery of some third alternative entirely, will likely determine how the cosmological constant problem is ultimately resolved. String theory, developed from the late 1960s onward and substantially expanded during the so-called superstring revolutions of the 1980s and 1990s, proposes that the truly fundamental constituents of reality are not point-like particles at all, but extremely small vibrating strings of energy, with different vibration patterns corresponding to different particle types, in a manner loosely reminiscent of how different notes emerge from a vibrating guitar string. In this framework, the properties of the vacuum, including its energy density, depend heavily on the detailed geometry of additional tightly curled up spatial dimensions that the theory requires beyond the three familiar dimensions of space, because there are an enormous number of mathematically consistent ways those extra dimensions could be shaped. String theory predicts not one single possible vacuum state, but an almost unimaginably vast collection of possible vacuum states, sometimes referred to as the string theory landscape, each with its own distinct value of vacuum energy and its own distinct set of physical constants. Estimates for the total number of distinct possible vacuum states within this landscape, based on counting the mathematically allowed configurations of the theory's extra curled-up dimensions, have been proposed by theorists including Raphael Bousseau and Joseph Polchinski to be as large as 10 multiplied by itself 500 times, a number so far beyond ordinary intuition that comparing it to the number of atoms in the observable universe, itself only around 10 multiplied by itself roughly 80 times, barely conveys the difference in scale at all. This landscape picture is part of what originally motivated the anthropic reasoning mentioned earlier, since if so many different vacuum states are mathematically possible, it becomes tempting to ask whether our particular one is simply the type of vacuum compatible with the existence of observers capable of studying it. Critics of this approach have pointed out that with such an enormous number of possible outcomes available, the theory currently struggles to make sharp, falsifiable predictions that could be tested against a single observed universe, a criticism that remains a genuinely active point of debate within the theoretical physics community. Loop quantum gravity, developed from the late 1980s onward, primarily through the work of physicists including Apayash, Carlo Rovelli, and Lee Smolin, takes a substantially different approach. Rather than positing vibrating strings living within spacetime, it attempts to quantize spacetime itself, treating geometry as something built from discrete, indivisible units, sometimes visualized as tiny interlinked loops forming what is called a spin network, at scales near the Planck length. In this picture, space is not an infinitely smooth and divisible continuum, as both classical physics and even ordinary quantum field theory generally assume, but is instead granular at its very smallest scale, made of distinct, countable units of area and volume, the way a digital photograph is ultimately made of discrete pixels, even though it appears smooth from a normal viewing distance. Loop quantum gravity has made specific, calculable predictions about what might happen to the vacuum and to the structure of spacetime generally, under extreme conditions such as the center of a black hole or the earliest moment of the Big Bang, potentially replacing the troublesome mathematical singularities predicted by classical general relativity with a smoother, quantum mechanically well-behaved transition instead. Neither string theory nor loop quantum gravity has yet produced a testable, experimentally confirmed prediction that would allow physicists to definitively choose between them, or to rule either one out entirely. And it remains entirely possible that the eventual correct theory will incorporate elements of both, or will look quite different from either current approach. What all serious contenders share, however, is the recognition that resolving the true nature of the vacuum, its energy, its possible granularity, and its relationship to the geometry of spacetime itself, sits close to the very heart of whatever a completed theory of quantum gravity will eventually need to explain. It is worth pointing out that physicists have not simply been content to theorize about the foaming, granular texture of spacetime at the Planck scale without ever attempting to test it. Between 2008 and 2017, a team led by the physicist Craig Hogan at Fermilab, the same American national laboratory renowned for its historic particle accelerator experiments, built and operated an instrument called the holometer, designed specifically to search for a predicted signature of quantum foam, sometimes described as holographic noise. a theoretical proposal suggesting that if space-time truly is granular at the smallest scales, that graininess might produce a subtle, correlated jitter detectable using extremely sensitive laser similar in basic design to the much larger instruments used by the Laser Interferometer Gravitational Wave Observatory to detect ripples in space-time from colliding black holes. The holometer used to overlapping interferometers, positioned to be sensitive to exactly the kind of correlated noise the holographic foam hypothesis predicted, and after several years of careful data collection, the experiment found no evidence of the specific signal it was designed to detect, placing strong new limits on that particular theoretical model of space-time granularity. This null result does not rule out quantum foam in general, since the holometer tested one specific proposed signature among several competing theoretical predictions for what Planck scale graininess might look like. But it stands as a genuinely important example of physicists taking one of the more exotic sounding ideas about the vacuum's deeper structure and subjecting it to a real, careful, technologically demanding experimental test, rather than leaving it as pure speculation. Other proposed approaches to probing physics near the Planck scale include searching for subtle irregularities in the arrival times of highly energetic gamma rays that have traveled across billions of light years, since even a minuscule graininess in spacetime could, over such enormous distances, accumulate into a detectable delay or spread in arrival times, depending on a photon's energy. An approach pursued using data from orbiting gamma-ray observatories. So far, no such effect has been convincingly detected either, but the search itself illustrates how even the most abstract-seeming ideas about the vacuum's ultimate structure remain tethered to the demand for real observational evidence. There is something quietly humbling in all of this. We tend to think of scientific progress as steadily converging on certainty, each discovery closing a gap in our understanding a little further. And in most respects, that is exactly what has happened with the quantum vacuum. We have moved, over the course of roughly a century, from imagining space as a featureless, inert backdrop to measuring, in real laboratories, the physical force exerted by its restless fluctuations. We have connected that same restless energy to the accelerating expansion of the entire observable universe. We have traced its influence down into the mass of the electron sitting in every atom of your body. And yet, at the very center of this remarkable body of confirmed knowledge sits an unresolved number, a gap of more than 100 orders of magnitude between what our best theories predict and what our best observations measure. A gap that no one has yet closed. Rather than undermining confidence in physics, this kind of honest, glaring discrepancy is exactly the sort of clue that has historically preceded the field's greatest breakthroughs. Unexplained anomalies in the orbit of Mercury eventually led to general relativity. Unexplained black body radiation eventually led to quantum mechanics itself. It is entirely possible that resolving the cosmological constant problem, understanding precisely why the vacuum's energy is so much smaller than naive theory predicts, will require, or perhaps reveal, an entirely new layer of physical law. One we do not yet possess the concepts to even properly describe. Several major observational efforts now underway or planned for the coming years are directly aimed at narrowing this gap between prediction and observation. The James Webb Space Telescope, which began science operations in 2022, was designed primarily to study the earliest galaxies and the formation of stars and planetary systems. But the extraordinarily precise distance and brightness measurements it enables for very distant objects also feed directly into ongoing efforts to pin down the detailed expansion history of the universe, complementing the work being done by DESI, Euclid, and the Vera-C-Rubin Observatory. Meanwhile, the Laser Interferometer Space Antenna, a gravitational wave observatory being developed by the European Space Agency in partnership with NASA and currently planned for launch in the 2030s, will consist of 3 spacecraft flying in a precise triangular formation millions of kilometers apart, sensitive to gravitational wave frequencies, entirely inaccessible to ground-based detectors like LIGO. Among its scientific goals is the search for gravitational wave signatures, potentially left behind by extreme events in the very early universe, including, speculatively, signals that could arise from a false vacuum decay process or an early cosmological phase transition of the kind discussed earlier, offering a possible future observational window into vacuum physics operating at energies and epochs no particle accelerator on Earth could ever hope to reach directly. It is also worth noting how young, historically speaking, this entire line of inquiry actually is. Serious quantitative discussion of the cosmological constant problem in roughly its modern form dates back only to a landmark 1989 review paper by the physicist Steven Weinberg, meaning the physics community has been wrestling openly with the full scale of the mismatch for scarcely more than 3.5 decades. A remarkably short span given how central the question has since become to cosmology, particle physics, and the search for quantum gravity all at once, compared to problems like the precise value of the fine structure constant, studied in various forms for over a century, or the search for a unified theory of forces, pursued since Einstein's own later decades. The cosmological constant problem in its current sharpened form is still, relatively speaking, a young puzzle, one whose most intense period of theoretical attention has coincided almost exactly with the career lifetimes of many physicists still actively working on it today. That youth cuts in 2 directions at once. It means the problem has not yet had anywhere near as much collective effort thrown at it as some of physics' other long-standing mysteries, leaving open the genuine possibility that a comparatively fresh idea, not yet fully explored, could still crack it open. It also means there is no guarantee that today's leading candidate explanations, symmetry, cancellation, dynamical dark energy, or the string landscape among them, will look anything like the eventual accepted answer. In the same way that early 20th century attempts to explain atomic spectra bore little resemblance to the full quantum mechanical picture that eventually emerged only after several more decades of persistent, occasionally frustrating work, none of this is likely to resolve quickly or neatly. The cosmological constant problem has resisted a full theoretical solution for over half a century, weathering the rise and fall of numerous proposed explanations. And there is no guarantee that a satisfying answer is close at hand even now. What can be said is that the questions themselves have grown sharper, more precisely defined, and more directly testable with each passing decade, moving from the realm of philosophical puzzlement into the realm of concrete observational targets that real telescopes and real detectors are, right now, actively working to pin down. Whether the eventual answer involves an unexpected symmetry that quietly cancels almost all of the vacuum's predicted energy, a dynamical field slowly evolving across cosmic time, a landscape of possible universes selecting for the rare ones capable of hosting observers, or some idea not yet imagined by anyone currently working in physics. The resolution, whenever it arrives, is likely to reshape our understanding of space, time, mass, and gravity all at once, precisely because the vacuum sits underneath every one of those concepts, rather than beside them. For now, the void above us, and the emptiness inside every atom of our own bodies, remains an open question written into the fabric of the universe itself, quietly fluctuating, quietly pushing galaxies apart, quietly waiting for a more complete theory to finally explain what it actually is. The next time you look up at a clear night sky and see the seemingly empty darkness between the stars. It may be worth remembering that this darkness is not a gap in the universe's story. Increasingly, it looks like the universe's story is being written there first. In the flicker of particles that appear for less than an instant, in the faint pressure between two plates in a laboratory, in the slow, steady stretching of space between galaxies that have nothing left in common but the emptiness that keeps pulling them apart. It is worth ending on the same note of honest humility that runs through the best of this kind of science, rather than on a false sense of closure. Every thread pulled on in this exploration, the Casimir force measured in a laboratory, the mass of the proton traced back to the churning vacuum of the strong force, the accelerating expansion first caught in the light of dying stars, the persistent, unresolved gap of more than 100 orders of magnitude between what theory predicts and what observation confirms, points toward the same underlying conclusion from a different direction. Empty space behaves like a physical system with its own energy, its own dynamics, and quite possibly its own deeper microscopic structure still waiting to be uncovered. Rather than behaving like a passive, inert stage with no properties of its own, that conclusion did not arrive through guesswork or philosophical preference. It arrived because physicists kept building more sensitive instruments, kept testing predictions that seemed almost too strange to check, and kept refusing to treat the word nothing as though it meant the end of the inquiry, rather than the beginning of a new one. There is a particular kind of scientific patience embedded in this story that is easy to overlook amid the strangeness of quantum foam and false vacuum bubbles. Casimir's prediction sat untested for the better part of 5 decades before the technology existed to measure it properly. Einstein discarded his own cosmological constant as a blunder, only for a very similar quantity to return under different physical motivation entirely 70 years later. The full scale of the mismatch between predicted and observed vacuum energy has only been appreciated in its modern, precisely quantified form for a few decades. A genuinely short span given how foundational the question has turned out to be. Progress on the deepest features of empty space has rarely come in a single decisive leap. It has come, instead, through a long accumulation of careful measurements, each one closing off certain possibilities while leaving others open, each one sharpening the next question rather than delivering a final answer outright. That is, in the end, a fairly accurate description of where the field stands today. Physicists do not currently know why the vacuum's energy density is so much smaller than the naive calculation predicts. They do not know, with certainty, whether dark energy is a truly fixed property of space or a slowly evolving field, whose behavior is only now beginning to come into observational focus. They do not know whether the deepest structure of space-time at the smallest conceivable scales is smooth and continuous, granular and foam-like, or something stranger still, built from relationships and information in ways not yet fully worked out, even in the more exotic corners of theoretical physics. What they do know, with a level of confidence built on decades of independently verified measurement, spanning laboratory tabletop experiments, orbiting telescopes, underground particle detectors, and observatories tuned to gravitational waves rippling in from across the cosmos, is that the question is real, that it is answerable in principle, and that the emptiness surrounding every star, every planet, and every atom of your own body is not a gap in physical law. It is one of the last great unclaimed frontiers of physical law itself, hiding in plain sight, in the spaces we spent most of scientific history overlooking simply because nothing seemed to be there.